We are, the panel is officially, we're going to Mars. And the question is, how the hell are we going to Mars? And I wanted to open this up because, Chris, I've interviewed you on stage a couple of times so far, Andy.
Yep.
But Chris,
Can't get rid of you.
I was looking at your bio and the research that you've done, and it brings up a very interesting question, and it's something that's been part of your focus is, what if we find some life already there on Mars? And this is a point of some contention, is that correct?
Yeah, it's a big deal. That's what we're going to Mars to look for, obviously, but we actually haven't spent much time thinking about what happens if we succeed. To me, it's sort of like the dog chasing the car. What is he going to do when he actually catches the car? Right? So we're searching for life on Mars, but what happens if we find it? Well, I think we could divide it into two categories. We find life that's related to us, no big deal, or we find life that's not related to us, really is alien, a second genesis, that's a big deal. Louder now? Okay, so the two scenarios. We find life that's like us on Mars, on our tree of life, no big deal. We find life that's alien, a second genesis, that is a big deal.
Now, when you say we find life that's like us, you're bringing up the possibility that life on Earth has come from elsewhere and has seeded much of our solar system.
Life could have exchanged between Earth and Mars.
Okay.
In the lobby of my building, there's a Mars meteorite. And we know that they came from Mars, and we know that they came in such a way that bacteria in those meteorites could have survived the trip. So the first astronaut on Mars, no offense, Andy, may have been a microbe launched by an impact 65 million years ago, for example.
And, well, like talking about a second genesis. Am I coming through? Yeah? Okay.
Yep.
Talking about a second genesis, it's a huge deal because, like, as he says, like, if Mars independently evolved life, so completely on its own, not infected by Earth, or Earth wasn't infected by Mars.
Can we turn up Andy's mic?
Yeah, I guess can I get louder, or I don't know.
Take that one.
Here. Is that better? Okay. Well, no? Okay. Well, if there is a second genesis, if there was life on Mars, then that means that life is incredibly likely, or at least it strongly implies that life is incredibly likely, because it means that on just two adjacent planets, I mean, Earth, we have the anthropic principle. In other words, the only reason we're wondering about life is because we are alive and we're on Earth. So Earth, from our point of view, functionally, Earth has a 100% chance of having evolved life because we wouldn't be there wondering about it if it weren't. But the next planet we visit, if it happens to also have life, that strongly implies that life is incredibly likely. And that's really important because that would mean that almost every planet, out there within a certain distance from its star will have life.
Now, but if you're going to look for life, and you're looking, and you find, and let's say you might have the possibility of finding a second genesis, what are you going to look for? How are you going to know it's life?
Well, that's the tricky part. How do you find life that's not like life as we know it? And it's a famous problem in science fiction, right? You get a tricorder, and that's how you do it. You all remember episode 26, of course, in the original series, where Spock uses a tricorder to detect silicon-based life. That's what got me into science, by the way, and I put aside basketball and started doing calculus. Right? But we don't have a tricorder. We don't even have a clue as to the principle at work. So it's a really important question. How do we recognize a second genesis of life, especially if those life forms are just microscopic? They're not going to be chasing us or running after us or running from us. They're just microscopic. How do we recognize? And that's actually the focus of my research. What should NASA do on a mission to Mars or Enceladus or Europa to recognize life and have the possibility of recognizing life that's not the same life as us? And we don't really have a good answer yet, but when I get home from this meeting, I'll get back to work on it.
But so if we let's say we find a second genesis, there's a really weird chance that we could accidentally wipe it out with our own biology. Isn't that correct?
That's right. So NASA has a policy called Planetary Protection, where if there's a chance for life on a world, then the spacecraft that go to those worlds have to meet certain requirements. And samples brought back meet certain requirements. And that's true. And those become a challenge when we send humans to Mars. Something you didn't address in The Martian, but obviously it's sort of implicit in there that you're there, humans are going to be spreading their stuff in the soil, growing potatoes, doing all the things that humans want to do.
Yeah, so what Chris is talking about is called planetary protection. The general concept is that we do a bunch of stuff with any probe that goes to Mars, and in fact, any object that might crash into Mars, anything on a trajectory that could put it in collision with Mars, has to go through these special decontamination procedures to make sure that it doesn't carry any little microbial astronauts to Mars with it. The concern is that Earth life could be an invasive species on Mars, same way that rabbits were in Australia. Seriously, that's the concern. I am sort of an outspoken opponent of the planetary protection policy, and this is a very contentious issue. So my opinion is just an opinion. It's just one of many opinions on the topic. But I have a series of questions that I always ask, where I say, like, okay, well, let's talk about this. Ask yourself the following questions to find out if planetary protection is worthwhile. So first off, is there any life on Mars? Is there any life, native or Earth genesis, whatever? Is there any life on Mars? If not, planetary protection is a waste of time. If so, okay, can any Earth life survive in Mars's environment? Seems kind of unlikely. It gets very cold. The atmosphere is almost a vacuum. There's nothing for it to eat. So then if the answer is no, then planetary protection is a waste of time. If the answer is yes, then could that invasive Earth life form find something to eat and reproduce such that it's actually taking over the Martian ecosphere? If not, waste of time. If so, okay, well then the next thing is, would that invasive species work? Would that invasive species take over the entire planet Mars, or would it just take over a region? Which, by the way, on Earth, in Earth's history, in Earth's ecological history, every time that's happened, the invasive species has taken over an area, but it's not like it's conquered the entire planet. So, and then finally the question is, if you believe all of that, do you believe that the probes we've sent so far were sufficiently cleaned? And I would say no. And then finally, do you plan to ever send humans there? If so, I mean, give up on not bringing bacteria with you when you send humans, right? So then the only question is, so now, proponents of planetary protection agree, yes, this is only for the period of time between now and when we first put humans on. We just want to get a look at what Mars life is before we screw it up. And that's fine. But I say you should definitely sterilize the hell out of any probe that's going there specifically to look for life. But probes that are not designed with that purpose, I feel don't need to be sterilized. So in the same way, if you get surgery in New York City, you definitely want the scalpel that the surgeon uses on you to be sterile, but you don't need a gas station in Bangladesh to be sterile. It's literally the other side of a planet.
I want to agree. I want to agree with everything Andy just said, but there's one question that he didn't ask, which is why I'm interested in planetary protection, and that question is, are we ever going to alter Mars to make it Earth-like in the future? If yes, then organisms we send there, even though they're not growing, as Andy pointed out, they're not spreading, will become part of that global biosphere. So if we ever want to terraform Mars, and I happen to be a big fan of that, then the stuff we're putting there now is potential inoculum on not Mars today, because as Andy points out, it's just not going to happen. Nothing from Earth can grow on Mars today. But in the terraformed world, then all these bugs that are inside our spacecraft now will see an Earth-like environment, and they will be able to grow. So to me, planetary protection becomes interesting when you ask the long-term question, what are we going to be doing with Mars in 100 years, 500 years, 1,000 years? Are we imagining it as a world full of life, biosphere everywhere? And then is that biosphere a gift from Earth, or is that biosphere the indigenous Martian biota, if it has one?
Now, I want to talk a little bit about what terraforming Mars is going to entail, but first, let's talk about why Mars. We keep talking about going to Mars. It's what we're all talking about these days, but why aren't we talking about building a base on the moon first to jump to Mars?
Well, I'm actually a proponent. I got to use better words. I'm a fan of that approach. I do like the idea of building a base on the moon first, with the theory that we would learn how to maintain a base off Earth in a gravity environment, in an environment where we're using local resources to augment supplies. I mean, we would learn all that stuff in a body that is effectively next door, the sort of place that you can abort to Earth. You can say, like, well, this didn't work. Everybody get on the ship. We're going home. before, and you can test all that stuff out in a realistic environment. So I would say, yeah, we should go to the moon again first.
Ditto. Everything Andy just said, ditto. I agree 100%. If it doesn't work on the moon, we're not going to be able to do it on Mars. Mars is a lot harder. Somebody once asked me, how many times harder? Put a rough number on it. I'd say it's easily 1,000 times harder to do it on Mars. Yeah, it's much further. As Andy pointed out, the moon stays right next to us. You can always do an Apollo 13 like abort to home. Whereas Mars, that just doesn't happen. And in the movie, you see the problems. The movie sort of, in Andy's movie, it sort of compressed the issue that the crew's got to fly a long time to get back to Mars. You know, it's sort of like 500 days later, they're there. And, you know, you're just sitting there and it's only 20 seconds has passed in your time. You don't appreciate how far it is and how hard it is to get there and back.
But doesn't the moon present some really special problems? Regolith is much more difficult to deal with than Martian soil, and the moon also doesn't have anywhere near the resources that Mars can provide in terms of sustainability.
That's true. And so if you're going to talk about colonizing as in a permanent human habitation that's going to live there, Mars is a much better target than Earth, because Mars has, in abundance, carbon, hydrogen, oxygen, and nitrogen, which are all the things life needs, a biosphere needs to spread and grow. So basically, you would have an infrastructure and an industry on Mars that builds your pressure vessels and stuff and expands your civilization out, but the actual biomass of, you know, all the humans plus all the plants plus all the bugs plus all the cats plus everything else you bring. I mean, of course you'd bring cats.
Cats on Mars?
Damn right, cats on Mars.
Really? Dogs? I think we should bring dogs
on
first.
Mars, that's fine. Whatever you like to eat, either way. So, just the entire biomass can only increase if you're bringing those elements in from the outside. And the way it works on Earth is like plants turn carbon dioxide and water and energy into hydrocarbons and release the unwanted oxygen. We turn hydrocarbons and oxygen and water into humans and release the unwanted carbon dioxide. And so that's how our biosphere works, but ultimately, you need that biomass to be added to your biosphere first. Mars has all of the elements you need. It has its atmosphere is made of carbon dioxide, and it has a bunch of water in the soil, and its atmosphere is 2% nitrogen. So it has everything you need. The moon doesn't. The moon has abundant amounts of oxygen. All the minerals on the moon are just huge amounts of oxygen. So if you smelt them, you'd get more oxygen out of them than you knew what to do with. But it has practically no carbon, practically no nitrogen, and very, very small amounts of hydrogen. So Mars is better to colonize, but the moon is better to visit and have a permanent, like Earth-dependent base on.
And just to make a plug for the current mission, the Curiosity rover discovered for the first time nitrate in the soil on Mars. Going back to Andy's point, Mars has got the elements for life. But the moon is a good place to test our ability to live off Earth. We've never done that. We should have bases on the moon just because it's nearby. We should be doing it, just like we have bases in Antarctica.
Also because it's awesome.
I'll go right to Mars, but I'll be going to Mars much happier if I know that the technology has been tested on the moon first.
I'm glad
someone
you agree.
out there is like,
yes.
Yes.
I second that, yes.
Preach it!
It feels like we're getting closer to going to Mars, but realistically, how close are we to sending the first human?
Well, NASA's, partly, I think, spurred by the book, The Martian, has announced that it is planning to go to Mars in the 2030s, right? And what a coincidence, about the time the movie came out, we had our first site selection activity down at Johnson Space Center. So there's at least talk about going to Mars and sending humans there. We'll see.
I'm a little more pessimistic. I think that I have no doubt that NASA could get to Mars in the 2030s if they had enough funding, but I don't have faith in Congress to give them enough funding. My guess is not too far off, though. I'm guessing more in the 2050 time range. And when I wrote The Martian, I shamelessly and just completely evoked feelings of the Apollo program. I did that on purpose. I made the Ares program look and feel kind of like the Apollo program to get those kind of like stirred up, yeah, Space America, booyah. But in reality, I think the first manned mission to Mars is going to be a large international effort, kind of like ISS. And it'll be us, the Russians, the European Space Agency, maybe the Indian Space Agency, hopefully the Chinese Space Agency if we can stop that kind of pointless non-cooperation, and JAXA, everybody who has a space agency, all working together, sharing the cost, and then sending something big and heavy to Mars. And so it's going to be a very, very different mission profile than most people imagine it.
One thing I'll point about on the cost is the costs may go down because of technology development on Earth that has nothing to do with space. Things like 3D printing, things like electric self-driving cars. Those will work on Mars. Gas cars, of course, won't. Things like the new toilets being invented by the Gates Foundation. You know, Google Blue Toilet. I want one for Mars. These are all technologies that are being developed to enhance sustainability on Earth, which will make it easier for us to design and build a base on Mars and the Moon that is less dependent on resupply from Earth. So sustainability is the word for the 21st century on Earth, the Moon, and on Mars.
So I would add that my opinion on what would really get us to Mars faster, the primary technology that needs to be developed is we need to develop technologies to get mass into low Earth orbit more cheaply. Right now it costs about $2,000 a kilogram. And I think NASA's going the right direction with this by funding multiple companies to work on their own booster technology so that there's competition in the marketplace for boosters. So you have ULA and SpaceX and Boeing, and they're all working to undercut each other, and that's what we want. I think if you look at the air travel industry, just aircraft, the vitriolic, hate-filled competition between Boeing and Airbus is the reason that air travel is cheap and affordable to the middle class. And I think that sort of competition among booster manufacturers is what will get us into space more cheaply. And once that happens, it'll drive the price of a manned mission to Mars down from like $100 billion to like $40 billion or something. And then the governments are like, well, you know, this is a little more reasonable, you know.
It begs also the question, when you're talking about international cooperation, it begs the question about how that cooperation takes place, that there needs to be agreement among all the countries that might visit Mars about the various protocols. I mean, that's a very complicated, I would imagine, international set of agreements to make.
Well, I'm sure Chris can tell you more about the details, but we've already made several of those agreements. The planetary protection is actually an international agreement. And also, in terms of just working together in space and the treaties involved in that, well, we already have a trial run at that with the International Space Station. So that's been NASA, Roscosmos, the European Space Agency, and JAXA. I may have left some out even, I don't know.
Yeah. But Andy's got a good point. The space station does provide one model. It's sort of a closed club, everybody live in the same house model. An alternative model could be the Antarctic exploration, where all the nations work together, but they each have their separate bases. But for example, the New Zealand base and the American base are just across the hill from each other, and they share fuel and power and airplanes and whatnot, but they remain separate, distinct bases. I actually think the Antarctic model might work better on the Moon and Mars than the space station model, but we have several models to choose from. But the point that it will be international, I think, is true. I don't think NASA will have a mandate to go to the Moon or Mars until other people go. The U.S. interest is being king of the mountain, but there's no point in being king of the mountain if there's no one else on the mountain, right? So when other people start going to Mars, to the Moon or Mars, private groups or other nations, then NASA will be charged to go too. So I'm a big supporter of SpaceX and all these other groups that want to go to the Moon and Mars. I say go, 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 because I know if they go, then NASA won't be far behind.
Well, also, I think it's great that China's getting feisty and sending probes to the Moon and stuff like that, because China is saying, like, yeah, we're going to do whatever we want. And so that's kind of spurring the U.S. to change some of its, well, very restrictive policies on private space flight. We have some I was talking to the guys at Moon Express who are trying to win the Google Lunar X Prize by being the first private entity to put a probe on the moon. And they said by far the biggest impediment, the biggest challenge to having a private entity putting a probe on the moon is policy. It's not technology, it's policy. They already know what to do, but there are all these like stumbling blocks and intervening obstacles put in the way by the U.S. government for rules that you have to follow if you're going to send something into space, which makes it much, much harder for them.
How close are we to a space elevator when you're talking about getting material past low Earth orbit?
Well, we're pretty far away from that because we need to invent something that has a much, much higher tensile strength than even like carbon fiber. I mean, the materials technology is the answer to that, but basically you have a minimum tensile strength necessary to maintain a space elevator, and we're nowhere near it.
That's actually, someone just pointed out to me that there is a theoretical length of rope that it couldn't hold itself up.
That's right, because if you just imagine a rope, well, it has a breaking strength, right? If I put a huge weight on the end of it, the rope will snap, if a big enough weight. Well, imagine that rope is so tall that the weight of the rope itself is greater than that weight. That means somewhere toward the top of the rope, it'll break off. And you say, well, no problem, we'll just use a thicker rope. Well, no, by using a thicker rope, you have now, if you make the rope, the cross-section twice as wide, you've now made the rope twice as heavy, and it'll break off at the exact same length. So the only variable here is the tensile strength of the material, the breaking strength. So it takes a certain amount of strength to break twine, it takes more strength to break steel, it takes even more to break carbon fiber. We need the next thing.
Kangaroo hide.
Kangaroo hide, obviously.
Just a small correction, twice as wide is 4 times as heavy.
I said twice the surface area.
Oh, okay, then you're right.
Wow, that was awesome. So, we're gonna have a nerd rap battle up here. Oh no, he didn't.
Well, it was interesting in the VIP room earlier today, the three of us sitting around with William Shatner and a quantum physicist.
Attempting to explain quantum probability to Bill, yeah.
And he kept saying, I don't understand this.
Yeah.
And he'd say, no, of course you don't understand, because it's counterintuitive. He's like, right, that's why I don't understand. Yeah. So why go to Mars?
Well, for me, the question is the search for life. Did Mars have life? We know that it had an Earth-like period when it had water and oceans and rivers and rain and all the things that we have on Earth that support life. Did Mars have life? And was that life a second Genesis? Because as Andy said, if we get to 2, we're done. Because there's a famous rule called the 0-1 infinity rule. And Isaac Asimov invoked it in his story, The Gods Themselves. That when you're talking about things in the universe, the only numbers that make sense are 0, 1, and infinity. You can have 0 life. We know that's not the case. 1, that's what we got. We know that we're at least at 1. If we get to 2, then we're at infinity. There's no logical or chemical or physical reason why the universe would have 2 lives or 3 lives or 4. It would have billions and billions and billions, essentially infinite. So the 0-1 infinity rule, if we can get to 2, then we've won. We know that the universe is full of life, and it's really cool. Let's go out and check it out.
So I have kind of 2 answers to that question, why go to Mars. The first one is the simple one. I'll start with that. I feel like we as a species need to have a permanent human settlement somewhere other than Earth, because although it's a very, very small chance, it's possible for a catastrophe to wipe out life on Earth.
Like a 6th mass extinction because of global warming?
A 6th mass extinction. Global warming wouldn't do it. I mean, whatever our problems with the ecology are, they're not so severe that we would suddenly wipe out all of humanity. But like a meteor impact or a killer plague or a solar event or something, I don't know. But it's possible for all life on Earth to be wiped out. However, if you have life on 2 different planets, our odds of extinction drop to nearly 0. So 25 years as a software engineer has taught me the value of backing up your data. That's the simplistic approach. The more complicated and nuanced one is I'll I'll try to go through it quickly because it's sort of a dull economic argument. But basically, it goes like this. First off, realistically, logically, if your goal and your objective is to learn scientific information about Mars, like Chris wants to do, there is no reason to send humans. It is so much easier and safer and better to send robots in every way. And the things that humans can do that robots can't, it would be much cheaper to develop robots that can do those things than it would be to send humans to Mars to do them. So you say like, oh, Curiosity can only go 200 meters a day, whereas an astronaut driving a rover could go, 20 kilometers a day. Fine. Instead of spending $100 billion to send an astronaut, spend $2 billion to develop a rover that can go 20 kilometers a day, and so on. So the only purpose to send humans to Mars, realistically, is to colonize Mars. So the question, and then I've already answered why I want to colonize Mars, but here's another reason to work on it right now. It's almost just to have an excuse to work on commercial spaceflight. It all comes down to that, because if the price to low Earth orbit in commercial spaceflight gets driven down to the point where a middle-class American can afford a trip to space, then there will be a space boom like the airline boom of the 20th century. It'll be a multi-trillion-dollar industry that grows around the world and will employ tens, maybe hundreds of thousands of people and bring a whole bunch of prosperity in. And it'll be this new explosive market. And so I know that's kind of a dry economic reason, and it's not really that exciting to a room full of people who dream of the stars, but that is a very practical reason.
Let me pick up on that. As I said, one interest in Mars is searching for evidence of life. But then there's life in the future. Can humans live and work on Mars? And as Andy says, that's the reason we need to send humans. And then the long-term future. Can Mars be made a planet full of life once again? Can we have 2 blue marbles in our solar system, like we may have had billions of years ago? To me, that's the ultimate question. And the question about past life and the question about human survival are just ways to understand how is the best to get to the long-term goal, which is a planet, a neighbor, that is once again a world full of life. And that's a goal, I think, worthy of a civilization that calls itself a spacefaring civilization.
Now, when you talk about finding either life that is similar to ours or a second genesis, do you have, for instance, when I look at extremophiles around the world, the amazing environments that life has been able to get a toehold, it makes me feel personally confident that life absolutely could have arrived here as a bacterium on a meteorite. Do you have an intuition about that? What is your feeling?
Well, if I'm objective and I look at the data that we have for Earth and Mars and the meteorites, I'm forced to the conclusion that the most probable answer is that Earth and Mars have a common biology. But there's a part of me that really hopes that it's alien, that we'll go to Mars and see something that's different as Chinese is from English. It may both be written on paper and both written with ink, and they're both books about how to build a table or something, but the basic way the information is stored and represented would be fundamentally different. That's what I hope. And that's what motivates me, is the hope that somewhere in our solar system we'll find life form that's so different from ours that we'll know that we're at 2. And then I can retire and let other people work out from 2 to infinity. Those are just details. It's going from 1 to 2. That's the big discovery. By the 0-1 infinity rule, if you get to 2, you can declare victory and retire. And that's my plan.
Is there, again, I'm not sure we got to this. Has NASA worked up rules for ways to look for life that doesn't necessarily behave like life we expect it to look like?
That's exactly what we're trying to do. And our first test of that, in fact, will probably be not Mars, but Enceladus. A moon of Saturn, has a plume, water coming from an ocean, slightly salty, full of organics. NASA just announced that we will be doing a New Frontiers competition that will include Enceladus. So I'm spending a lot of time working on what would we do if we got a sample of that plume, how would we detect life? And to just go into some details, I think our best hope is to search for amino acids, look at their distribution, and look at their handedness. And if you want to know the details of that, talk to me later, but it could be a general signature of life that's different from us, but still lives in liquid water. A second genesis that is still using the same fundamental chemistry of water that life on Earth is using.
Yeah, I never thought of that. The opposite chirality would pretty much prove it.
Yeah, right. If life on Enceladus was all right-handed, we are all right-handed. By that I mean that the amino acids and the proteins in your body are all left-handed. If we go to Enceladus and find lots of amino acids and they're all right-handed, that would immediately tell us that it's a completely different origin of life, and that would be really cool.
Okay, I'll bite. What does that mean? Left-handed and right-handed amino acids.
Okay, this is your left hand. This is your right hand.
No, this is a good way to describe chirality.
Okay.
He's not screwing with you.
Do it. Andy. You could probably explain it more simply.
Well, if you imagine the shape of a molecule and then imagine looking at it in the mirror, and then you magically pull that one out of the mirror, those two molecules are not identical. One of them's a mirror image of the other, like your right
Stereoisomer, is that what they're called?
Yeah. Yeah, stereoisomer. So if you look at your left and your right hands, they are the same, but they are mirror images of each other. You can't just hold your hands up next to each. You couldn't put your left hand on your right arm. Well, you could, but you wouldn't look normal. And so that's what chirality is. It means it's like a three-dimensional mirror image of the other one. Now, when your DNA generates amino acids, and when it does, it generates them in a specific way. So, this is what this amino acid looks like. It's this molecule, and it's an asymmetrical molecule. And then if we found that amino acid in the flipped version, the other chirality, then that would mean some form of life.
By the way, that's something we've never found on Earth.
Some of them will, but
we
most
do
of them
find
won't.
right-handed amino acids, and some of them are used in biology, but not in proteins. Some toxins are right-handed amino acids.
Thalidomide.
Yeah, and some of the cell wall structures in bacteria. But in proteins, it's only left-handed amino acids.
Right, and because it has to do with the spiral of our DNA and the way that it assembles proteins. And so if we found the other-handedness of proteins, that would mean some other life form is assembling these proteins in a way that our DNA literally can't. But amino acids are actually fairly small, simple molecules. They may be critical to life. They may be something that absolutely has to evolve in order for life to exist. So it may be that we find completely independently evolved life that has the same amino acids we have. And then how would we know whether or not it was independent or just a descendant of Earth life or vice versa? And the answer is, if the chirality is opposite, it's definitely independent.
Yeah, I want to make a comment here that you guys will all understand, which is this picture of chirality, sort of driving on the same side of the road, all the molecules are the same handedness, we think is a completely general feature of life. That complex molecules will always have chiral centers. Life will always have to decide, is it going to go left or is it going to go right? And it's my best guess that that is how a tricorder works. The physics of a tricorder. It does so by detecting chirality, which can in principle be detected remotely by looking at the scattering of microwaves. So, if you go to Lawrence Krauss's book, The Physics of Star Trek, tricorder doesn't appear in the book at all, right? So I'm going to write Larry and say, here, physics of tricorders, chirality, remote detection, here's how it works.
Here's sirs.
I'm now totally interested in what the ASL sign is for tricorder.
Oh.
All right.
Yeah, you can see them. I take my job as trying to invent a tricorder, right, and put it on a massive mission and detect life. Hopefully a tricorder that will detect alien life as well as Earth-based life.
I think she's spelling it out. She's doing something different.
It's always everybody has a style.
You two have to fight.
ASL
It's
rap
stereo.
battle.
It's stereo.
ASL rap battle.
So you mentioned earlier, Chris, terraforming Mars. And that means literally making the atmosphere acceptable to life.
Correct.
How would such a thing happen on the order of any time scale that's reasonable?
Well, the fundamental challenge in making Mars a place suitable for life is warming up the planet. Now, that's something we know how to do. We're doing it on Earth.
Nuke it!
We're doing it.
So we sent Rupert Murdoch first?
It turns out, if you do the numbers, if we are to do on Mars what we're doing on Earth already, which is putting greenhouse gases, super greenhouse gases in the atmosphere, at the same rate roughly that we're producing them on Earth, That the same thing will happen on Mars that's happening on Earth, which is the planet will warm up by a few degrees per decade. And in 100 years, you're there. Now, that's not there for humans. That's there for life, anaerobic plants, small microorganisms, things like that, some insects. The oxygen buildup takes much, much, much longer.
Well, also, Mars is blessed with a huge amount of carbon dioxide at the poles, so you heat that up, and that's a greenhouse gas. So it would actually create a runaway effect, which is what you would want in that case.
How would you start heating that up?
Well, Elon Musk says we should nuke them.
That doesn't work. The physics of that is it doesn't work. If you work it out, the only way we know how to, yeah, I'm sorry. We've nuked the Earth several times with tests, atmospheric tests, and that hasn't made it hotter. What's made the Earth hotter is slow, steady production of greenhouse gases. That's the way you warm up a planet. We've learned that lesson on Earth, and that's the way to do it on Mars as well. So we've demonstrated that technology.
You'd maybe send a reactor or something that would just sit there and heat. No, this time I'm not joking. You'd send a reactor or something that would just like heat polar dry ice and just release more and more. No?
No, the problem is if you heat one place where there's ice, that ice will evaporate there and then just recondense elsewhere where it's cold. You've got to put a blanket over the whole planet. And that's what greenhouse gases do. If you just heat one spot, the volatiles will just move from that spot to another cold spot.
5-minute warning.
5-minute warning.
I was talking about heating up carbon dioxide to release that. It's a greenhouse gas. That wouldn't work.
Well, the easiest way to do it is to put extra greenhouse gases in the atmosphere, because right now the carbon dioxide wouldn't stay in the atmosphere. It's still too cold. It would just recondense at the other pole, just like it does every year.
We would bring it? We would bring the
No,
carbon dioxide?
it's way too much to bring. Even if you're making it at the parts per billion level, you've got to mine it there. And this was another big discovery of curiosity that's relevant. It was the first detection of fluorine in the rocks and soil on Mars. Fluorine is the molecule of choice in these greenhouse gases, not chlorine, not bromine, because they destroy ozone, whereas perfluorocarbons don't. So we'd want to make it out of carbon and fluorine. We know there's carbon in the atmosphere. Now we know there's fluorine in the rocks and soil, although we were pretty sure it was there anyway. So we would make it there, release it in the atmosphere, and as Andy said, the system is positive feedback. You heat it up, CO2 comes out, that adds to the greenhouse, that heats it up. So in 100 years, on that sort of time scale, you would have a planet that's blue and green with life.
100 years?
100 years. Now, it would not be humans walk out in a shirt sleeve. The air would not be breathable. You'd have to have a mask providing a source of oxygen, but you would not need a spacesuit. And you'd be able to grow potatoes. Just right there in the field. That's the food of choice now. We are really doing experiments at Ames, growing potatoes under Mars-like conditions. Now, I won't tell you where we got the inspiration for that experiment, but he's sitting right next to me.
Sweet potatoes, though, right?
Yeah, I've actually been told that sweet potatoes would have been a little bit better of a crop.
Okay, well, we're working with the International Potato Center. There really is a place in Peru.
Oh, just
here at the IPC.
Just another puppet of the powerful potato lobby. Just
They have eyes everywhere. Oh.
Yay!
I died a little inside.
All right. Well, we can't close with the dad joke, so I'd love an answer from each of you as two folks who've spent a lot of time thinking about getting to Mars, what it's going to be like when we get there. What discovery made about Mars do you find most exciting, Chris?
Water. It once had water. That's the reason why I'm interested in Mars, because water is what life on Earth needs. All organisms on Earth need water, liquid water, to grow or reproduce. So water.
Same answer, different reason. Water, but not, hey, it once had water. More, hey, it has water right now. I'm excited about that because for every cubic meter of Martian soil, there's about 35 liters of water in it.
Wait a minute. Every cubic meter of Martian soil has how many liters?
35 liters of water. So if you were to fill your refrigerator with Martian soil and then pull out all the water that's in it, you would have 35 2-liter bottles full of water. So this is great because I'm more interested in the much more short term, like sample return missions and stuff like that. Chris is already like setting up who's going to be king of Mars like later on down the line. But I'm more focused on like the short-term stuff like sample return missions. And water, the massive abundance of water means that if you have water and carbon dioxide, both of which are now, we know, abundant everywhere on Mars, you can make rocket fuel with a chemical reaction called the Sabatier reaction that basically turns water and carbon dioxide into methane and oxygen, plus energy, And that means that you can send an empty rocket and some harvesters, and they would go collect the materials necessary to make fuel for the rocket to come back. And that's a huge boon for a sample return mission. So that's what I'm excited about.
Yeah, right on.
I want to also do a special thanks. We had a dropout, and Chris only agreed last night to come and be our guest panelist here with Andy to talk about Mars. So please give him a hand.
It's because I'm local. I'm at NASA Ames, which is just down the road, and it was easy. It was by coincidence. I was driving down the highway, and Woz was on NPR talking about this conference. And then I get home, and there's an email from Kristen saying, "Could you come and cover for NASA on this so that we don't look bad?" And I said, "Sure."
I thought it would be improper for the feedback loop to just be me and Andy, who seem to have been on stage at least 5 times in the last few weeks talking about Mars. Please give a big hand to Andy Weir.
Thank you.
I'm Adam Savage. Thank you guys so much for coming out.